So friends, as we are away from each other, for your kind information, I am Dr. S.K. Tiwari, Adjunct Faculty, Department of Geology, Institute of Science, Banaras Hind University. I welcome you all in this talk which is on groundwater water quality and aquifer information system. So before going into the deep of this talk, it is essential to understand the journey of rainwater to the subsurface. The rainwater or the surface water which flows on the soil before percolating into the subsurface formations, they cover their journey from different types of soil horizon or different type of rocks. It also moves through different formations with different residence time in different type of formations before reaching to the groundwater reservoir or into the actual groundwater system or the aquifer systems or in the saturated zone. The groundwater during its journey from surface to subsurface condition gains total dissolved solids in their journey. If they move through the barren or massive granitic formation, the total dissolved solids in such type of water will be less in comparison to the water which crosses or moves through the hornblende biotite gneiss type of formation, where the TDS will be of moderate nature. While if the groundwater crosses through the schist, limestone, etc. at shallow water level, in such type of groundwater we will get more total dissolved solids. So the quality of groundwater depends upon various factors, that is their journey from different type of rock formations, their residence time before actually reaching to the saturated zone or to the aquifers. The quality of groundwater will be different in different areas. For example, in the hilly terrains where the recharge is more, we get good quality of groundwater. While in plains where the recharge is less in comparison to the hilly areas, we get moderate type of groundwater because of the increment of salt in such areas. In shallow, where we have shallow groundwater table, there we get high evaporative and transpiration. And in such areas, the groundwater will have high salt content, especially in canal command areas. For example, in the Ganga Yamuna Doab, which is in Punjab and Haryana, has led to salt incrustation on soil and makes such type of groundwater difficult for agriculture. Now, there are various natural nutrients which are present in groundwater. These nutrients are chemicals containing elements like nitrogen, phosphorus, carbon, sulfur, calcium, potassium, iron, manganese, boron and cobalt, which are very essential for the growth of living things. Some are required in small quantity and these type of elements are known as micronutrients. Some of the nutrients are required in large quantity and these are known as macronutrients. The carbon is obtained from the carbon dioxide which is present in the atmosphere, while the nitrogen and phosphorus is obtained from the soil or water. These nitrogen and phosphorus is also derived from the municipal or industrial wastewater, which if added to water bodies result in algal blooms or eutrophication, which is unnatural accelerated growth of algae. And because of this algal bloom or eutrophication, the available light becomes limited and the algal cells begins to die. This increases decomposable organic matter in the water body, resulting in consumption of oxygen and deterioration of water quality. There are various chemical parameters to understand the quality of water. The common cations which are present in groundwater includes sodium, potassium, magnesium and calcium. The common anions which are present in groundwater are in little amounts. These are chloride, sulphate, bicarbonate and carbonate. Some other parameters are also taken into consideration while going to talk about the quality of groundwater. These include iron, boron, nitrate, fluorine, phosphate and silica. Sometimes Acidified water samples are also collected to find out natural or artificial pollutants like iron, lead, arsenic, zinc, mercury, chromium, etc. Now, if we are going to talk about the quality of groundwater, it is very essential to understand the method of sampling, how to sample the groundwater from the field. In the sampling, we need Pyrex glass or polyethylene bottles to collect the water samples when we go to the field. Normally, for the analysis of water quality, we need a bottle of 1 to 2 liter, because for analyzing the various parameters to understand the quality of groundwater, we need 1 to 2 liters of water sample. After collecting the water sample from the field, they are stored in cool place. If samples have been taken from wells, they should be collected after the pumping of well for some time. It is essential to record the different depths from where the samples have been taken, the size of casing, the date of collection, the water temperature during the collection of sample, the order, the color, turbidity, and the operational condition of the well. For organic and radiological constituent, special sampling and storage techniques are used. Some of the parameters can be analyzed in the field. For example, the temperature, the pH, alkalinity, dissolved gases, and the cations like iron, copper, aluminium, manganese, chromium, and zinc can be analyzed in the field using the field kits. So, again, before going to talk about the quality parameters of groundwater, it is essential to understand the various units of measurement. The various units which are commonly used for the measurements include milligram per liter, which is equivalent to parts per million, milliequivalent per liter, which is equivalent to ppm, millimoles per liter, electrical conductivity, pH, TDS, salinity, hardness, acidity and alkalinity, and for organic matter, the parameters or the units are BOD and COD. So, the milligram per liter, what does it indicate? What we mean by milligram per liter? So, it is equivalent to ppm by weight, that is, the parts per million by weight is same as milligram per liter when density of water is 1. Similarly, milliequivalent per liter of sample commonly used in all types of hydrogeological calculations and diagrams. ppm, that is equivalent per million by weight, is same as milliequivalent per liter when density of water is 1. Millimoles per liter of samples used for ionic activity calculation. So, I'd like to tell you, friends, that the salt content in normal groundwater is very less in comparison to saline or brackish water. The electrical conductivity is measured in terms of mu mho per centimeter or mu Siemens per centimeter and normally measured at 25 degrees Celsius. The electrical conductivity can be measured at site by electro conductivity meter. This is related to the ions which are present in solution, and this EC varies from salt to salt. For example, the equivalent conductance of sodium and calcium bicarbonate solution is around 100 mu Siemens per centimeter per ppm, while the potassium chloride solution is around 150 mu Siemens per centimeter per ppm. That is, we can say that the EC varies from salt to salt. So, taking normal groundwater composition of calcium bicarbonate type with some NaCl, the electrical conductivity can be obtained by multiplying 100 with ppm, either anions or cations. Now, another unit or parameter is pH. This is a very important characteristics as far as the quality of groundwater is concerned. They are hydrogen ion concentration and represented as pH. The hydrogen ion activity range between 10 to the power minus 4 to 10 to the power minus 10 for natural water and are expressed in pH units, where pH is a negative of log of hydrogen ion activity. pH of natural water range between 4 to 10, the average being 6 to 8.5. The pH is neutral when acidity of hydrogen ion is equal to hydrogen ion. That is, we can say that at pH 7, the pH is neutral and the activity of H ion, that is the hydrogen ion, is equal to hydroxyl ion. But we know that the hydrogen ion behavior is temperature dependent, and this value, that is the value of H ion, decreases with increase in temperature. So water with excess of hydrogen ions are acidic in nature and they have pH less than 7. And the water with excess of hydroxyl ions are alkaline in nature and they have pH more than 7. So we can represent pH as pH is equal to minus log of hydrogen ion. Now we will talk about total dissolved solids, which are normally measured in milligram per liter. The total of concentration of all the dissolved constituents or substances or salts in a water sample is known as total dissolved solids. That is, the aggregate salts are measured as TDS, that is total dissolved solids. These substances in solution exist in their ionic form. The cations which are commonly present in groundwater includes calcium and magnesium, and these two cations are mainly responsible for the hardness of groundwater. The other cations normally present in groundwater includes sodium and potassium. The important anions which are present are chloride, sulphate, bicarbonate and carbonate. The other ions may be present in a smaller concentration like boron, iron, manganese and nitrate. These ions can be calculated from the electrical conductivity by multiplying it with 0.64. So water with less than 1500 milligram per liter total dissolved solids are considered as fresh water. So salinity is normally total dissolved solids, which expresses the concentration of ions in a solution. It can be measured with an electrical conductivity meter and is commonly used for strong electrolyte solutions such as seawater and brines. Like TDS, the salinity can be expressed as milligram per liter, but often they are expressed as ppt. The salinity, that is the saltiness or dissolved salt contents of a water body, it is technically defined as total mass in grams of all the dissolved substances per kg of water. The different substances which are dissolved in water, they give different taste and odor to the groundwater. The salt content is an important factor in water use. In fact, the humans and the other animals have developed various types of senses which are to some extent able to evaluate the potability of water and are avoiding water that is too salty in nature. The salinity always exists in groundwater, but it is variable in amount. It is mostly influenced by aquifer material, the solubility of minerals, the duration of contact and factors like permeability of soil, drainage facilities, quantity of rainfall and above all the climate of the area. So these are some factors on which the salinity is dependent. The salinity of groundwater in coastal areas may be due to airborne salts originating from air-water interface over the sea and also due to over-pumping of fresh water which overlays saline water in coastal aquifer systems. The Bureau of Indian Standard has recommended a drinking water standard for TDS, a limit of 500 milligram per liter, which is corresponding to about electrical conductivity of 750 S per centimeter at 25 degrees Celsius. That can be extended up to TDS of 2000 milligram per liter, corresponding to about 3000 S per centimeter at 25 degrees Celsius, in case if there is no alternate source. So water having TDS more than 2000 milligram per liter are not suitable for drinking uses. The electrical conductivity values in S by centimeter at 25 degrees Celsius of groundwater from observation wells can be used to show the distribution pattern of salinity in different ranges of suitability for drinking purposes. It has been observed that majority of the waters having EC values less than 750 S per centimeter at 25 degrees Celsius occurs mostly in few of the states of our country, and these states are Jammu and Kashmir, Himachal Pradesh, Uttarakhand, northern part of Uttar Pradesh, Kerala, Sikkim, Chhattisgarh, Orissa, and western Ghats of Maharashtra, Karnataka, and northeastern states. So water with electrical conductivity ranging between 750 to 3000 S per centimeter at 25 degrees Celsius falling under permissible range are confined mainly in only few parts of the country. These areas where we get the water with the EC ranging between 750 to 3000 S per centimeter are Uttar Pradesh, MP, Bihar, West Bengal, Andhra Pradesh, Karnataka, Tamil Nadu, Maharashtra, Jharkhand, Punjab and Manipur. In some cases, relatively high values of ECs in excess of 3000 S per centimeter have been observed in many parts of the country. Now, with the qualitative measurement or with the expression of salinity, we can categorize the groundwater into various categories. So, if the salinity is between 0 to 1000 milligram per liter, they can be classified as fresh groundwater. If the salinity varies between 1000 to 10,000, they can be categorized as brackish water. If the salinity varies between 10,000 to 1 lakh milligram per liter, they can be categorized as saline water. And if the salinity is around 35,000 milligram per liter, they are similar to sea water. And if the salinity is more than 1 lakh, they are categorized under brine water condition. Now, another parameter for the measurement of or for understanding the quality of groundwater is hardness, which is represented by H. The total of ions which can precipitate as hard particles from water is known as hardness. Mainly the divalent cations are responsible for the development of hardness. So hardness is nothing but the sum of calcium, magnesium and sometimes iron. All are divalent in nature. They are expressed as calcium carbonate equivalent per liter. Thus, hardness can be defined as calcium into calcium carbonate by calcium plus magnesium into calcium carbonate by magnesium, where hardness, calcium, magnesium are measured in milligram per liter and ratios in equivalent weight. So hardness can be defined as Ca into 50 by 20 plus Mg into 50 by Mg, or this can again be represented as hardness is equal to 2.5 calcium plus 4.1 Mg. Hence, the addition of calcium and magnesium in milliequivalent per liter multiplied with 50 gives total hardness in milligram per liter. So on the basis of the hardness, we can again categorize the various type of water. The hardness is normally measured as concentration as calcium carbonate and represented as milligram per liter. If the hardness is between 0 to 60, they are categorized as soft water. If the hardness range between 60 to 120, they are categorized as moderately hard water. And if the hardness range between 120 to 180, they are classified as hard water, while if the hardness is more than 180, they are classified as very hard water. The hardness is again of two types. That is, they can be classified as temporary and permanent hardness. The temporary hardness is because of the calcium and magnesium concentration, which are balanced by bicarbonate, all expressed in milliequivalents per liter, and thus precipitate as carbonate by simply heating. This can be represented by the equation Ca and Mg plus bicarbonate giving calcium carbonate and magnesium carbonate. The permanent hardness means the part of calcium and magnesium in excess of bicarbonate, all expressed in milliequivalent per liter. Now we'll talk about other parameters like alkalinity and acidity. Alkalinity means its ability to react with hydrogen ion, its ability to neutralize acids, and alkalinity is determined by titrating with acid down to a pH of about 4.5. This is equal to concentration of bicarbonate plus 2 into carbonate millimolecules per liter in most of the samples. Acidity is its ability to react with hydroxyl ion. Also, it is an base neutralizing capacity. This is determined by titrating with alkali up to a pH of about 8.3, and it is equal to carbonic acid concentration in most samples. Another parameter is organic matter. Normally we know that the organic matters are of two types. The first category is biochemically decomposable or degradable organic matter, and the other category is not decomposable organic matter. The common parameters for characterization of organic matter are BOD, COD, volatile solids. All these reflect the aggregate organic constituents. Now what is BOD? BOD is nothing but the amount of dissolved oxygen which is needed or demanded by aerobic biological organisms to break down the organic material present in a given water sample at certain temperature over a specific time. It measures oxygen equivalence of organic matter. The BOD test measures the first type of organic matter, that is the biochemically decomposable or the degradable organic matter. The another parameter is COD, chemical oxygen demand. This is measured as chemical reduction of permanganate or dichromate solution and expressed as oxygen equivalent. The COD and volatile solids measures the total organic material. Now we'll talk about the various natural chemical constituents of groundwater. There are various chemical constituents which are naturally present in groundwater. These are sodium, potassium, calcium, magnesium, carbonate, bicarbonate, chlorides, sulphates and nitrates. Now we'll try to see them one by one, how they are present in the groundwater naturally. The first one is sodium. This is the sixth most abundant element which is present in groundwater. Most rocks, soils, minerals and plants, water and foods, they contain sodium compounds in the form of sodium chloride. They are mostly found as non-toxic metal in natural water. But if their amount becomes excess, they can cause a bitter taste and is harmful to cardiac and kidney patients. They are corrosive to metal surfaces and in large concentration they may be very toxic to plants. The sodium can be tested at concentration of 200 mg per liter or more. The source of sodium are mainly the erosion of salt deposits and sodium bearing rock minerals. So because of the erosion of these deposits and because of the passage of surface water to the subsurface rocks through the sodium bearing rock minerals, the sodium is released and this sodium becomes enriched in groundwater. Second one is naturally occurring brackish water of some aquifers in nearby of the groundwater aquifers. The saltwater intrusion into wells in coastal areas. Another one is infiltration of surface water contaminated with salt. Another one is irrigation and precipitation leaching through soils high in sodium. Another source is groundwater pollution by the sewage effluents, and also they are derived from the infiltration of leachate, that is the water that has percolated through a solid and leached out some of the constituents present in the rocks or minerals from the landfills or industrial sites. Another naturally occurring substance or element is potassium. They are very commonly found in soil and various types of rocks. The potassium have no taste and they do not have any color. The source of potassium is weathering and erosion of potassium-bearing minerals such as feldspars. Feldspars, as we all know, that feldspars are very rich in potassium. Another source is leaching of fertilizers. By the excessive use of fertilizers also we get heavy amount of potassium in soil. Another source of potassium is seawater in areas susceptible to salt water intrusion. As we know that potassium is positively charged ion. It may be adsorbed by negatively charged colloidal components of soils and rocks. That is, for example, silicate clay minerals, iron and aluminum oxides and organic colloids. All these can adsorb potassium. The extent to which the potassium will be adsorbed depends on nature and amount of colloids present. For example, peat having a large number of highly charged organic colloids will adsorb considerably more potassium than sand, which has few colloids. Another naturally occurring substance is calcium, which is the fifth most abundant element in groundwater. These are obtained from the weathering of rocks, mainly limestones, marble, calcite, dolomite, gypsum, fluorite and apatite, and from soils through seepage and leaching and runoff. The average concentration of calcium in soil is about 1.37 into 10 to the power 4 milligram per kg. The leaching of calcium from soil increases significantly with acidity of rainwater. The concentration of calcium in water depends on the residence time of water in calcium-rich geological formations. The surface water also contains lower concentration of calcium than groundwater. The availability of calcium depends upon the solubility of various compounds such as calcium carbonate, calcium phosphate and calcium fluoride. The solubility of calcium carbonate is 14 mg per liter, which increases 5 times in presence of carbon dioxide. The solubility of calcium phosphate is 20 mg per liter, while the solubility of calcium fluoride is 16 mg per liter. The calcium is a very good determinant of water hardness because it can be found in water as calcium ions. Magnesium is the other hardness determinant. The magnesium is the 8th most abundant element which is present in groundwater. If magnesium is present in groundwater, they will give unpleasant taste. This taste can be observed at 100 to 500 mg per liter, and a sensitive person can easily identify this unpleasant taste. The magnesium may have a laxative effect, particularly with magnesium sulphate concentration above 700 mg per liter. The other parameters are carbonate and bicarbonates. The primary source of carbonate and bicarbonate ions in groundwater is dissolved carbon dioxide in rain and snow, which as enters the soil dissolves more carbon dioxide which is present in the soil. An increase in temperature and decrease in pressure causes reduction in solubility of carbon dioxide in water. The decay of organic matter also releases carbon dioxide. The pH of water indicates the form in which carbon dioxide is present in water. The presence of carbonic acid, bicarbonates and carbonates indicate the type of water. If carbonic acid is present, the groundwater will be having pH less than 4.5. If the groundwater is having bicarbonates, the pH will vary between 4.5 to 8.3. And if the groundwater is having carbonate, the pH will be more than 8.2. Now, under usual condition, the bicarbonate may range from 100 to 800 ppm in groundwater. Another parameter is sulphate in groundwater. We all know that sulfur in atmospheric precipitation is about 2 ppm only. But the wide range in sulphate content in groundwater is through the oxidation process, precipitation, the solution and concentration as water traverses through different type of rocks. The primary source of sulfur is sulfide bearing minerals in the igneous and metamorphic rocks, and the minerals like gypsum and anhydrides which are present in sedimentary rocks. In addition, the heavy use of fertilizers and soil conditions also plays great role in its abundance in groundwater. The reduction of sulphate by bacteria and precipitation of gypsum may also cause removal of sulphate from groundwater. The another parameter is chloride. It is important in groundwater, though its presence in crustal rocks is very less. That is, it is present in the rocks in insignificant amount. The processes like evaporation and dissolution of salts, contact with evaporatic bodies, presence of entrapped water during sedimentation, and seawater intrusion causes high content of chloride in groundwater. The chloride salts are highly soluble and free from chemical reaction with minerals of reservoir rocks and remains in NaCl form. However, the chloride concentration may exceed than that of sodium due to the base exchange processes. The calcium and magnesium chloride rich groundwater are quite rare. The abnormal concentration of chloride in groundwater will be or may be due to sewage and industrial wastes. This diagram shows the presence of chloride in the groundwater in different parts of our country. Another parameter of significance which is present in groundwater is nitrate. The minor constituent, this is a minor constituent of rocks, but this is a major constituent in atmosphere. It enters to groundwater cycle by the electric discharge during the process of lightning in the sky. The average concentration of nitrate in rainwater is only 0.2 ppm, and hence its average concentration in groundwater remains below 5 ppm. So, the main contribution of nitrate comes from decay of organic matters, sewage wastes, and use of fertilizers. Hence, the high concentration of nitrate is found in only local areas, or we can say that they are found in localized areas only. The diagram shows the presence of nitrate in groundwater in various parts of our country in more than 45 mg per liter quantity. So with this, I would like to thank you all for your patience for listening this talk, and have a nice time again. Thank you.